Okay, so chapter 25 is over fluid and electrolytes, and we'll do some acid and base problem stuff. I know y'all probably want me to go over some of those, right? Y'all did those in lab. I know you're going to have some of those questions in lab, right? Okay. So a human body, 45 to, I'd say 75% fluid. 45 to 75% fluid. And it's the rule of thirds. So your extracellular fluid is only 1/3. And the other 2/3 is considered your intracellular fluid. Okay, intracellular fluid, what is the intracellular fluid? That's your what? Fluid inside the cell, right? So we need to be aware of ion concentrations within these two basic compartments because they're essential for fluid balance. Bless you. So just so we're clear, extracellular fluid, that's like what? Your blood plasma. And what else? Interstitial fluid. Good. And we said this is fluid within the cell. Okay. I drew this line down here so that we could divide what's within the cell and then what ions are found in the biggest concentrations outside in the extracellular fluid. So we won't divide them here between the blood plasma and interstitial fluid because the concentrations are roughly the same for ions. Okay? So the main cation found in the extracellular fluid, can you think of what it might be?
Sodium.
Yep. Good old sodium. Good old sodium. I think it's like 145 millimoles per liter, or milliequivalent, whatever it is. So if you want to do like the alligator sign where it's bigger on the extracellular fluid, or concentrations of the extracellular fluid versus the intracellular fluid. And that's a positive ion, so that's considered a cation. It's the big cation in the extracellular fluid. Now the big anion in the extracellular fluid happens to be chlorine or chloride ions. It's about 115 milliequivalents or millimoles per liter. That's the anion. This is a cation. And an ion is what again? What's an ion? What's an ion? Oh, what? I heard it.
An atom with an electrical charge.
Perfect. Atom with an electrical charge. Electrical charge. Positive or negative charge. Okay, so these are ions. Now, what about in the intracellular fluid? We need to talk about the components or the ions that are most prevalent or in highest concentrations in the intracellular fluid. That would be potassium. Potassium is a cation or an anion? Cation. It's like 155, I think is its number, something like that. And we usually talk about like potassium levels. It's only like 98% of it is found within the intracellular fluid, and only like 2% of it is found within the extracellular fluid. So I think the number you probably learned was like 3.5 milliequivalents. That's normal potassium levels, right? So even just a slight change in potassium levels can make you feel pretty crappy or cause heart arrhythmias, right? Yep. So yeah, that's a cation. The big anion is actually phosphate. You also have a lot of proteins within the intracellular fluid that give it a negative charge. As far as ions go, we'll talk about it as phosphate because it's an electrolyte. Okay? That's an anion. I think it's like 105. Okay. There's another one, magnesium. It's an important ion for chemical reactions. It's found more so in the intracellular fluid, in a higher concentration in intracellular fluid. But the main four that you need to know are sodium, chloride, potassium, and phosphate. Okay? Oh, and calcium. Where do you think that is a higher concentration? Extracellular or intracellular? Yeah, extracellular. So make sure you know these four. Okay. Just going over some terms for fluid balance before we dive into pH. Fluid balance is just how much water you're taking in, how much fluid you're taking in, and then how much you're getting rid of. That is fluid balance. In its most simplest terms, that is fluid balance. How much you're taking in and how much you're getting rid of. So that is normal intake or fluid intake. I think your book may call it just fluid intake versus fluid output. And those two must be equal for you to be in fluid balance. Right? So what you take in must equal what you put out for there to be fluid balance. If it is not, then it is imbalanced or unbalanced. Okay. There are some terms, they call them preformed or metabolic. Preform is just the ingested fluid, so what you're taking in, and make it sound all fancy. And metabolic is the fluid that you make through metabolic processes, so through like aerobic cellular respiration. Do we make water as a byproduct? We sure do, so that's the water coming from there. And together, we make about, I think it's, let me make sure these numbers are right, milliliters a day. And this one is only like 200 milliliters a day. And add those together, this is the total normal intake. Okay? So then what should be our normal output, or fluid output, if we are in fluid balance? It should be equal the intake. So it should be this, if we are in fluid balance, right? How do we get rid of fluid? First thing comes to mind is we pee it out, right? Urine, and that only takes care of about 60% of it. How else? So we have left, what, 40%. How else do you think we get rid of sweating? Sweating? What else? Yeah, through your breath. There's fluid loss through your breath. Okay? So the other 40% is lost through other means. There's actually some water loss through feces as well. In these terms, obligatory water loss or facultative water loss. This right here, obligatory water loss, happens no matter what. You can't stop it. So it's like your body says, we got to get rid of this fluid. I don't care how hydrated you are or dehydrated you are. This is what your body gets rid of no matter what happens. It doesn't matter how hydrated you are or dehydrated you are. Okay. Now, facultative water loss, it depends on hydration. It depends on hydration. And can we think of something we've already talked about that helped to control fluid loss when we talked about our nephrons? When we talked about our nephrons in the collecting duct and distal convoluted tubule, we talked about two things, basically. We talked about hormones. Remember the hormones that help to control fluid loss? What was one of those? ADH, right? So hormones. We'll just say hormones regulated in the nephrons of the kidney. Okay. So it's worth noting that facultative water loss, it will help to decrease your fluid output, with your antidiuretic hormone, but only to a certain point, because no matter what, we still, over time, we will, lose fluid due to obligatory water loss. Okay? So it'll help us, facultative water loss will help us decrease fluid output when we're dehydrated, but not inhibit completely water loss or fluid loss because of obligatory water loss. Does that make sense? So I guess just know those terms and what they mean. All right. So before we move on to pH, there's basically 5 things that affect fluid balance. The first 4, the easiest way to understand these is that the first 2 depend on, I guess you could say they have the same concentration. Or is the concentration, you would ask, is the concentration the same? And then these 2, you would ask, is there a change in the concentration? Okay, I'll show you what I mean by that. The first one's called volume depletion. Volume depletion. Okay. So the first 2, concentration is the same. Concentration is the same. First 2 we talked about, concentration is the same. Now, volume depletion is like whenever you get a severe burn, you have like chronic vomiting or diarrhea, or we could say hyposecretion of aldosterone. That could result in volume depletion. Basically, with volume depletion, it is your fluid loss. Your fluid loss is greater than your fluid gain, right? But we're talking about fluid here. We're not talking about solutes, right? Because concentration stays the same, osmolarity stays the same, but it is movement of fluid. That causes this imbalance. Now the next one's called volume excess. It's sort of the opposite of this. It's where fluid gain, is greater than fluid loss. Okay? Could we think of something where this might happen? So if volume depletion could result from hyposecretion of aldosterone, this could result from hypersecretion of aldosterone, right? Or renal failure. But renal failure is, so if your kidneys aren't working right, it means you're not getting rid of enough fluid, right? Renal failure, not getting rid of enough fluid. So here, the concentrations stay the same. Now the next 2, we see a change in concentration. Dehydration. You've all heard of dehydration, right? It's basically when fluid loss is greater than solute loss. Okay, so imagine when fluid loss is greater than solute loss. So what's going to happen to our blood? Yeah, concentration is going to go way up. The osmolarity is going to go way up with the dehydration. What's something that could lead to dehydration? Excessive, basically sweating, yeah, where you're losing a lot of fluid but not losing the solutes, right? Diabetes can actually lead to this. Diabetes mellitus, we're going to talk about that later. Alcohol consumption or hyposecretion of ADH can also lead to this. And then the last one of these four, and then we'll talk about number 5, is hypotonic hydration. You're like, what? Sounds like an oxymoron, doesn't it? Hypotonic hydration. This is like when people poison themselves with too much water. Water intoxication. This is basically water intoxication. So when you have water intoxication, it's typically followed by a whole lot of sweating, right? So what would be the blood situation here? So instead of too much fluid loss, we had too much fluid gain. Yeah, so it's basically the opposite. You could also get this from ADH, hypersecretion. Okay. What happens to your cells in this situation? They swell. Right? They swell. So I didn't write this out, but water gain is greater than solute gain. Okay, water gain is greater than solute gain. Let me make some room for number 5. Number 5 is fluid sequestration. I think that's how you pronounce that. Forgot an E. So what's different from this is that the total body fluid, your total body water, your total body fluid is typically normal. That's not messed up. But where it's distributed, fluid distributed abnormally. So the fluid is distributed abnormally. So the total body water, total body fluid is typically normal, but where it's distributed is typically weird or abnormal. And we could imagine that would result in something like what? Edema. Could result in something like edema. Or with liver failure, could result in ascites. When it is around the heart, it's called pericardial effusion. Okay. What about if it was not around the heart but the lungs? Yeah, I was thinking plural effusion. Plural effusion. Make sure you know this one, at least. Fluid sequestration. Now we get to talk about pH. You excited? Yeah, so excited. Okay. What'd y'all learn normal blood pH as? So yeah, probably 7.35 to 7.45, right? I think it is actually even more precise, and it's really 7.38 to 7.42, right? We'll use this one though, just so you're aware. Okay. If you like ever saw that on like blood work or anything like that, ABG or something, that's an arterial blood gas, ABG. All right, so this is blood pH. Now we know pH, what's the range, what's acid-base pH range? 0 to 7 is neutral, and then it goes all the way up to 14, right? So from 7 to 0 is considered acidic. From 7 up is considered basic or alkalinic. Okay. So basically the way I wrote this is that from 7.35 or from 7, from this range right here, from 7.35 to 7, that's considered an acidosis. So you know what I mean by that? From 7.35 to 7, that area is considered an acidosis. If you go past 7, it's not good. All right? You will die. Now on the other end, from 7.45 to like 7.7, that would be considered an alkalosis. All right, past 7.7, yeah, you'd be dead. Okay. So some symptoms or signs, from being in this range, 7.35 to 7, when you're acidotic, you'd be sluggish. And if it's bad enough, you could be in a coma. Now on the other end, alkalosis, your muscles start to become twitchy. And they get cramps, muscle cramps. Now what's a muscle we would not want to have a cramp in? Well, yeah, I was thinking more like your diaphragm. But you probably your diaphragm. Would you want that to cramp up? No, because if your diaphragm cramps up, then you can't breathe, right? So you learn basically 3 tools that your body uses to manage pH. You went over these. I think you watched a video, filled out a little thing in lab, didn't you? You say yes.
Well, it's for our Thanksgiving.
Oh, you're supposed to. So you're lucky I'm going over this. I'm helping you out. So the first one, this is like the super fast system. It's super fast, but easily overwhelmed. And it deals with short-term changes in pH, and that is your buffer system. That is your body's buffer system. And what is the main buffer in your body? I know I've written this equation on the board before. It's basically, we'll just say bicarbonate. But your body does. You know, your body reabsorbs about a pound of baking soda, or can absorb about a pound of baking soda in a day. Sure does. Insane. All right. So, it's easily overwhelmed. It deals with short-term changes in pH. You don't even know what's happening. Now, the majority, like 75% of our pH problems are dealt with by the respiratory system. Okay. And you wouldn't even notice because, like whenever you yawned right there, I was waiting for somebody to yawn. It changes in a couple of breaths. When you take a big sigh or you yawn or something like that, that is basically your respiratory system accounting for ups and downs in your pH. There's somebody yawning again. It's crazy, isn't it? In a couple of breaths. So the last one that does the best job, but seems to take the most time, is the kidneys. Okay, it's the kidneys. So your body uses all of these three tools to manage your pH, your body's pH. So I can't help it. I got to write out this equation. Oh, you remember that? Should. You better know that equation. So look, well, here's our buffer. Here's our buffer. And your body's like, oh man, we'll take that all day long. Because that buffer, if we have an increase in the buffer, it'll take these hydrogen ions and convert them finally to water and CO2. And your body's like, oh man, I would take that any day over an increase in these hydrogen ions because that would make us more acidic, right? But there's a point in which this becomes easily overwhelmed and something else has to take over, either your respiratory system or your kidneys. So that is why the bicarbonate system is easily overwhelmed. There's a point in which that buffer system is like, too much, right? Like it becomes, saturated. It can't handle anymore. Okay? Make sure you know this equation. So I think I just mentioned your kidneys, they basically can reabsorb about a pound of baking soda, sodium bicarbonate. Most of the reabsorption happens within the proximal convoluted tubule. So, that's what we're going to look at first. So here's the lumen. Here's the lumen, and this then would be, the interstitial space. We're cool with that? And this will be our proximal convoluted tubule cell. And then this is the blood. This is our PCT, proximal convoluted tubule cell. So we're talking about bicarbonate. Right? And that's just hanging out in the lumen of the tubule. And we want to reabsorb that and get that into the blood. That's our end goal. You have these transporters here. These special mechanisms, transporters, that will actually exchange or pull in sodium. It's pulling in that sodium there, right? It's reabsorbing that sodium in exchange for, guess what? Hydrogen ions. Hydrogen ions. You're like, wait, do we want those hydrogen ions there? You remember that equation we wrote out? What do hydrogen ions and bicarbonate make? Let's do that. Yep. Well, these PCT cells, the proximal convoluted tubule cells, they actually have our good old friend carbonic anhydrase. You remember that enzyme? The carbonic anhydrase? Carbonic anhydrase. It's an enzyme that takes bicarbonate and hydrogen ions and turns it into, let's see if I can do this, and turns it into CO2 and water. Yeah. We just skipped a little step. Then these can just diffuse into the cell. And they meet our friend carbonic anhydrase again and dissociate into bicarbonate and, I gotta get the right color here, hydrogen ions. That's how we get it into the cell. Now, where was our end goal for bicarbonate? We wanted to reabsorb a pound of baking soda, right? All right, so we got to get our sodium and our bicarbonate into the blood. But we have these little co-transporters, our little co-transporters here, that are going to co-transport bicarbonate and our sodium. Okay. Basically, sodium moves down its concentration gradient, and with it, it pulls along bicarbonate. Does that make sense? It's all those concentration gradients, always concentration gradients that help move things along. There's one thing left in the cell here that we forgot about. Good old what? Hydrogen. He's stuck over there by himself. But remember, weren't we exchanging hydrogen for sodium? Look, he's going to go on out, and we're going to continue to pull sodium in. So that's basically how we are able to reabsorb a pound of baking soda in a day. Okay? So this is, general. We're not really fine-tuning our filtrate here. There are different cells that help to fine-tune our filtrate in order to maintain pH. And that was with our distal convoluted tubule and then our collecting duct. So we already talked about principal cells. Remember, those are the ones that were associated with hormones. Now these are just what they call intercalated cells. Intercalated cells. The other ones were principal cells. These are intercalated cells of the DCT and collecting duct. Okay. And I could have drawn these one on top of the other like they're next to each other, but I thought it was easier to see them separate. Okay. So we have like two flavors. Like here's flavor A and flavor B of these intercalated cells. Type A is going to react to situations in the blood that are acidosis. So then we would think that type Bs are going to react to situations that are alkalosis. Okay? They're basically the same. They're basically identical cells except for where they're going to place their transporters. right? Because remember, we're talking about things that affect pH, so like hydrogen ions and bicarbonate ions. So we're going to want to put those in different places. Does that make sense? I'll show you what I mean. We're going to keep track of certain ions. We're going to keep track of our hydrogen ions. We'll keep track of course, bicarbonate, HCO3 negative. We'll keep track of chloride ions. And then one we haven't seen yet, potassium ions. Okay? And this just says A and B cells are identical, except for where they put their transporters. So if type A is reacting to acidosis, where are we going to, like it's acidotic within the blood, where are we going to want to put the bicarbonate? Back into the blood, right? So our transporter for bicarbonate needs to go here. And it needs to go this way. And it happens to exchange for chlorine. Okay? There's another transporter on the other end that pulls the hydrogen out and puts it where? Into the lumen. Because we want it out of the blood, right? In exchange for potassium, right? But we can't leave the potassium in the cell. It ends up in the blood through its open channel. Potassium usually always has some sort of open channel. So in this situation, we're going to reabsorb potassium ions in order to decrease what? Hydrogen ions. That's helping to correct our acidosis. Does that make sense? If not, we're going to do the reverse, so maybe that'll help. So if it's reacting to an alkalosis in the blood, where our blood is basic, a basic pH, where are we going to want our buffer to go, our bicarbonate? On the luminal edge, right? This way. Because by doing so, then what is going to come in? Chloride ions. And then on the interstitial edge, that's close to the blood, who's going to be added into the blood eventually, reabsorbed into the blood? Hydrogen ions in exchange for potassium. But we can't leave potassium within the cell. It has an open channel, and it gets... Is that reabsorbed? Is that process reabsorbed? It goes back into the filtrate, so we call that secretion. Remember, reabsorption is back into the blood. When it is the other way, in specific, it is considered secretion. All right, so we secrete potassium ions in order to increase hydrogen ions in the blood, raising pH. All right, so know what each type of cell does. I will ask you a question about this. So, I mean, you also have some carbonic anhydrase in here. That enzyme is typically there whenever there's bicarbonate and hydrogen ions, because they have to interact with each other. So it's there mixing things up, putting things back together and apart, and so forth. Okay? So I thought I would bring up diabetes because it is pretty prevalent. And it applies to one of our acid-base problems. Okay. So there's another type of diabetes, diabetes insipidus. It's called diabetes insipidus. It doesn't have to do with insulin. It's different than diabetes mellitus. It has to do with typically, or it's caused by ADH hyposecretion. ADH hyposecretion. So like where it's not enough is coming from the postpit, or the kidneys have an inability to react to ADH. So if they're not reacting to ADH, or there's not enough ADH, what's that going to do to fluid retention? You're not going to keep enough fluid, right? And with diabetes insipidus, you're not keeping enough fluid and you're getting rid of a lot of urine. So in other words, you're losing a lot of fluid volume with diabetes insipidus. It's something like 3 to on upwards to like 20 liters a day. That is a lot. Considering we only are supposed to lose like what? What is it, like 1.5? It's not very much. If left untreated. So that's diabetes insipidus. Now, diabetes mellitus, the mechanism for that, there's basically 3 categories for that we'll talk about. Okay, diabetes type 1, sometimes it's referred to as DM1. DM just stands for diabetes mellitus. You can be genetically predisposed, like a family history of it. There could be some environmental triggers, but essentially it results from an autoimmune disorder. Okay? An autoimmune disorder. So, like, this is your pancreas, and the beta cells of your pancreas, which are the ones that make insulin, remember, are being attacked. You make antibodies against your beta cells, and eventually your beta cells no longer work, so you're not making insulin. Okay? They call this insulin deficiency, an insulin deficiency. Now with type 2, you can be genetically predisposed. Can be related to obesity and hypertension. It presents typically, but not always, in adulthood. We're seeing it younger and younger these days. Type 1 typically presents in childhood. I'll go ahead and talk about the miscellaneous category. It is either drug-induced or gestational diabetes, which means it's associated with pregnancy. Okay? So both of these are sort of in the same category in that they're considered insulin resistant. Okay? This one was insulin deficiency, right? If you're insulin deficient, it prevents the production or secretion of insulin into the blood. Correct? Now, if you're insulin resistant, you have the inability of cells throughout the body to actually respond to insulin. Your cells have an inability to respond to insulin. Okay? And this can progressively get worse. So in some sense, it is a relative insulin deficiency. But in both senses, you need insulin. Okay? Let me show you what I mean by that. So how does this insulin mechanism work? It's responding to an increase in the concentration of glucose, right? Where is it going to act on? What's its target? The pancreas. What cells of the pancreas? Beta cells. Okay. Beta cells are the ones that make insulin. And insulin goes and works on body cells. Correct? And in turn, what do we do to our glucose? Those body cells take it up thanks to insulin. And we reduce glucose concentration. Now, where type 1 comes in is here. And type 2 and the miscellaneous, here. Does that make sense? So typically when this is working normally, this is a negative feedback mechanism. But if it is interrupted either at this stage or at this stage, then there are problems. This pathway is disrupted, and glucose stays in the blood and concentrations go up, and it results in hyperglycemia. Okay? Now, the way in which I want to relate this to your acid-base problems is with basically type 1. With diabetes type 1, diabetes mellitus type 1, you have low insulin, right? And cells are forced to shift from glucose metabolism to fat metabolism. Does that make sense? Because if you can't take up glucose because you don't have the insulin, you have to metabolize something for energy. And so instead of metabolizing glucose, you metabolize fat. And when you metabolize fat, you start to make these keto acids. And those keto acids, if that increases enough, can result in ketoacidosis. I know you learned about, or you will learn about that in lab. Okay, that is one of our metabolic acidosis issues or disturbances. Okay, we'll get there. So to talk about this, we need to know the difference between a fixed acid and a volatile acid. So fixed acids are those produced from a metabolic process. Okay. Therefore, it's going to be regulated by which mechanism? The respiratory system or the kidneys? Okay. And they do this by reabsorbing bicarbonate and hydrogen ions. We just talked about that. Okay. So one way in which your body does this in the GI tract can produce these fixed acids from animal proteins in wheat, lactic acid, from glycolysis, and phosphoric acid from nucleic acid metabolism. And we just talked about one. Keto acids, that is metabolism of what? Fats. Yeah, so keto acids, that's a type of fixed acid, and it's made from metabolism of fats. Okay? So this was, sorry, animal proteins. And I think wheat. Okay, so those are controlled by the kidney, reabsorption of bicarbonate and hydrogen ions. Now, the volatile acids, that's basically what? H2CO3. That's the volatile acid, and it's produced from expired CO2 or evaporated gas. This is going to be regulated by which system? Obviously, yeah, the respiratory system. Okay? So this regulated by the kidneys, reabsorbs and eliminates bicarbonate and hydrogen ions and volatile acids produced from CO2. Okay? So make sure that you understand that. Which falls in which category. Now we can move on to your acid-base disturbances and problems. You want to talk about those? Because I know you have to do some. Okay. Well, when learning your acid-base disturbances, you have to know the normal values. You already know what pH is. 7.35 to 7.45. That's the first thing you always look at. Then you look at your volatile acid. That's controlled by the respiratory system, your CO2. What's normal value for that? 35 to 45. And then your bicarbonate, your fixed acid, which is, yes, 24 to 28. Or did y'all have 22? 24. Yeah. Depends on your book. Okay. So we have 4 main categories here. Respiratory acidosis or respiratory alkalosis, metabolic acidosis, or metabolic alkalosis. Okay? If it is a respiratory acidosis, you're going to see a higher than normal CO2. Okay? If it is a respiratory alkalosis, you're going to see a lower than normal CO2. So lower than 35. Respiratory acidosis is the most common of all the acid-bases disturbances. It can be caused by things like trauma and infection. So if it's trauma, it could disrupt the nerves that are involved in breathing or airway obstruction, or even just a decreased gas exchange can result in respiratory acidosis. Okay? On the flip side, if you have a lower than normal CO2 and it results in respiratory alkalosis, this could just be from severe anxiety or high altitude, being at a high elevation. CHF. What's CHF? Congestive heart failure, severe anemia, or even an aspirin overdose. Okay. So now if it is a metabolic problem, meaning the kidneys are the problem, okay, then you will see a lower than normal bicarbonate, If it is a metabolic alkalosis, it'll be a higher than normal bicarbonate. Does that make sense? This metabolic acidosis is where we get that keto acidosis. And that was related to what type of diabetes? Type 1 diabetes. Okay. What type of acids contribute to metabolic acidosis that are formed from glycolysis? Lactic acids. Acetic acid. You drink too much alcohol, you can produce what's called acetic acid. That can also contribute to metabolic acidosis. Renal dysfunction, and also severe diarrhea. And then finally, metabolic alkalosis, vomiting. Too much diuretic. That causes you to lose too much fluid volume. And taking large amounts of antacids can lead to metabolic alkalosis. All right, enough of that. Let's do some examples. You ready?
No.
Yes, you are. I'm going to show you how to do it. Easiest way to do it. You can do it. Everybody got this?
No.
Okay. We'll do the first one here. Okay, so let's say pH is 7.48. CO2 is 25. And bicarbonate, CO3, is 20. All right? So what I want you to do is write basically that many blanks. Okay? 2 blanks on top and then 1 blank on the bottom. This is the first blank that you're going to fill out. And it is going to tell us about our pH. It is, according to our normal value, it is considered an alkalosis or an acidosis. It's high, so it is an alkalosis. Almost there. It's half of it. Now we want to talk about this blank. We need to determine if it is respiratory or if it is metabolic. You follow? The very next thing you look at is the CO2. Don't even look at your bicarbonate yet. I don't care about that right now. Okay? So now you look, you know it's an alkalosis. So now look down at your chart. And so if your CO2, if respiratory is the answer, if respiratory is causing your alkalosis, your CO2 should be lower than normal. Is that what's happening? It sure is. So what is that first blank? Respiratory. Now, this last blank, you need to fill in whether or not you have compensation. That means the other system is trying to fix the problem. That's what compensation means. It's like one is causing the problem and the other one is trying to fix it. So if respiratory is causing the problem, then hopefully the kidneys are trying to fix it. So how do you figure that out? You know what you have to do? You just look at your bicarbonate. If it is normal, then there is no compensation. If it is not normal, then there is compensation. AKA, if you have a normal value, then there is no compensation. Maybe write that down. If you have a normal value, there is no compensation. So 20 for our bicarbonate is what? Is low, so we must have a compensation. How do we write that? With what kind of compensation? Do we say metabolic? No, we say renal compensation. Why do we say that? Remember, metabolic is causing, it's a metabolic issue, whereas the kidneys are renal and trying to fix the issue. So that's basically why you write renal instead of metabolic. Okay? Pretty easy. If you know your normal values, you can do this. You want to do another one? Okay. Let me erase this. Okay. Let's say our pH is again 7.48. CO2 is 55 and bicarbonate is 33. What's the first thing you look at? Your pH. pH says it is an alkalosis. Okay? Now we need that first blank, so we look at our CO2. We don't look at bicarbonate. CO2 is what? It's high. Does that explain our alkalosis here? According to our chart, sure doesn't. So then, is our first blank respiratory? No, it's metabolic. I didn't even have to look at bicarbonate, did I? Nope. Now, I need to see if we have something compensating. So I look at this value and I see, is it a normal value? No. It shouldn't be because it's a metabolic problem anyways. So if there are no normal values, then we say it's with, it needs to be opposite of our problem. So it is with respiratory compensation. Remember, if one is causing the problem, the other is trying to compensate for it or fix it. Okay? Cool. That's all I have. So test on Monday. On Monday, happy studying.